everyone. So the title of today's lecture is the Lichtenbaum-Klun property, but that's a bit of a lie, because that's what it's supposed to be according to the schedule for the third day, but I want to finish up the discussion from last time. I'm not sure exactly how long that will take. So maybe in the second half of the lecture we'll talk about the Klun-Lichtenbaum property. But first, so recall we were proving soft theorems. There's one, Lon, Matthew, Meyer, Tama. So for n bigger than or equal to 0, that the Tn plus 1 local K theory of R, or A, I'll say, you can localize height n plus 1 on the inside. There's also Clausen, Matthew, Naumann, Noel. So this is maybe also n bigger than or equal to 0. If Ltn R is equal to 0, then and A is an associative ring spectrum.
Even okay, not necessarily.
Yeah, it could be non-connective. It could be whatever you like. And then there was, so this is CMNN in the P group case, Clausen, Burklund in general.
So there was also a question I had about this distinction between Quillen K theory and the non-connective Thomason, Bold, and so on. So you said that after localization they coincide because the negative, I mean, there is this phenomenon that you see only the sufficiently connective part. But I have also a related question just to clarify. So for usual ring, they are related in the sense that the Quillen BJ plus cos this is just a connective part of the full thing. But when you have a ring which is a ring, simplification ring or a ring spectrum or non-connective, is it related in the same way, or is
for connective ring spectra it is, but otherwise no.
Otherwise, it's they are not it's not the connective part of the full thing, but still after localization is the same.
Well, no, not necessarily. We'll see. We'll see actually.
So this is for the Quillen type construction, or I don't know exactly.
No, I said the official definition I was going to take for K theory was going to be the one based on perfect complexes. Yeah, but if my ring is connective, I'm allowed to use the Quillen instead.
Okay, and this does not say the negative of Thomason, Trobo.
Yeah, the question of whether it, again, that part doesn't matter. That part doesn't matter because I'm doing these telescopic localizations. So I don't whether you can take either connective or non-connective. I don't care. It's gonna be the same after I telescopically localize. But it is important when, in principle, it is important that you do it K theory based on perfect complexes when you have a non-connective ring. Whether you take that to be the connective K theory or the non-connective K theory is not important. But we will make a remark about this in a little bit. Okay, right. Yeah, so this is that if A to B, so P V1 Vn minus 1 complete Galois extension of Tn local rings. With group G finite. Then when you go to the next height, you get descent. And the background for all of this, well, maybe not this one exactly, but the background for these two at least is this redshift philosophy of Ausoni-Rognes, that if R is kind of most interesting at chromatic height n, then the K-theory of R should be most interesting at chromatic height n plus 1. Right. So, and I said that the ansatz of giving proofs was that I was going to give the proofs in the simplest case, which illustrates the proof in general. And here it was the...
So the first reference you wrote, CMNN, the P group case?
Oh yeah, P group case, yeah.
Okay.
Yeah. Okay. Right, and we gave the proof, well, we gave the proof of the first one in the special case where n equals 0 and A is an ordinary associative ring. Now I want to give the proofs of these or analogs of these for ordinary commutative rings. But actually I first have to make a preparation about pure chromatic homotopy theory, which is one of the most important aspects of telescopic chromatic homotopy theory, and that's something called Tate vanishing. And it relates to a question that Ofer asked yesterday. So let me make a recollection about something called the Tate construction. So say G is a finite group. And let's say C be a stable infinity category. Let's say with all colimits and limits. Then if we have X in C with an action of G, so maybe more precisely that would be X in the functor category from BG or point mod G to C. Then you get a natural map from the orbits to the fixed points, so to speak. So formally, this would be the colimit over this diagram, and this would be the limit over this diagram. But if this were ordinary category theory, you would call this the quotient by the group action, and this the kind of fixed object by the group action. And this map is sometimes called norm, sometimes called trace or transfer. I'll call it TR. So, well, intuitively, what you have to do is you have to make a mapping from an orbits to a fixed point. So this should correspond to a G cross G, or a GG, you know, a equivariant for G on the left and G on the right. That should, and then for this you take the sum over G and G of the action of G on X, of the given action of G on X. That's just intuitively. And the notion of being able to sum a map makes sense because you're in a stable infinity category, or really just a semi-additive infinity category, one where initial and final object agree and finite coproduct is the same as finite product. And then the cofiber of this transfer map is called the Tate construction, so denoted XTG.
Okay, so this is like the construction used to define so-called Tate cohomology for an action of a group.
Exactly. So, for example,
groups, it's like you have a bounded complex of G modules and.
Yeah. So let's say C is the derived category of abelian groups, and let's say X is an abelian group in degree 0. Then that, you know, then with an action of G, so it's just a G module in the usual sense. Then XG, since we're taking this colimit in the full derived category, this is a complex computing the group homology of G acting on X. And this is a complex computing the cohomology of G acting on X. And then this TR is the usual, well, usual map in degree 0. So in this case, the data, this lives in non-negative degrees, this lives in non-positive degrees. So this is just the usual connecting, the usual transfer map in degree 0. And then this XTG is a usual complex computing Tate cohomology. So that's yeah. Now there's a very important structure. So suppose so C has a symmetric monoidal tensor product commuting with colimits in each variable. Like normal, like for example, smash product on spectra or tensor product there, then this Tate construction functor is lax symmetric monoidal. And in particular, it sends rings, so it sends rings to rings. Modules to modules. This is not obvious from the definition. The claim is something like, for example, let's suppose X is actually an algebra object equipped with a G action. This is sort of clearly an algebra object. You're taking the fixed points. And the claim is somehow that this is behaving like an ideal. This transfer map is behaving like the inclusion of an ideal, so that when you take the cofiber, you actually get a ring. It's not obvious at all from this definition, but there are other definitions that make this more plain. I won't get into the details of that.
So also when you say the word lax, so a priori you can see it 2 ways.
Yeah, but I specified which way. There's only one way which makes that parenthetical comment true. Yeah.
But is it true that the word lax can be used to designate both?
I don't know, but I've made it unambiguous by saying this.
Okay.
The other is called oplat.
Yeah.
What?
I think the other is called oplat. Oplat.
Okay, I'm switching to yellow chalk. Okay. Right. So now here's the, I think in my opinion, it's the most important result about telescopic homotopy theory. So homotopy theory working at a fixed height. So this is a theorem of Nick Kuhn. So G is a finite group. P is our fixed prime. They were always doing our chromatic homotopy theory at. And n is a height. N is a natural number indexing height greater than or equal to 0. Then the Tate construction is always 0 in this Tn local category. So if you take C to be this Tn local spectra, and you have an object there equipped with a G action, the Tate construction is always going to vanish. Equivalently, so say X, so if this lives at heights less than or equal to n, then the Tate construction will live at heights less than or equal to n minus 1. So the height n information will vanish, and it'll be pushed down. So this is also known as blue shift. Whereas algebraic K theory had the opposite property, or is supposed to have kind of the opposite property of redshift, that the heights go up, here the heights go down. Okay, let's do just a couple of examples. So, well, first example is when n equals 0, then LTNSP is just this algebraic thing, derived category of Q. Then you have, well, we have this transfer map, like I said. But then you can also include into X fixed points and project back down there. And then you get a map the other direction.
So just to clarify again, because maybe so about this localized thing is for spectra. So first you localize the spectra at P. You consider P local, and then you mod by P, then by V1, and then suppose you get 0 at some stage, then this is what you call, or
no, that's
another discussion about the technical.
Yeah. So what is the
product of different?
Yeah. So this guy in here is going to be PV1 up to Vn-1 complete. So it's complete along these guys, and then when you take it mod PV1, Vn-1, and Vn, then you get 0. So Vn acts invertibly on X mod PV1 up to Vn-1.
But ln f.
Yeah, that would be just, ln f would be just this condition, without this condition. Yeah. Yeah, you're welcome.
So in this theorem, there are no assumptions in X.
That's correct. That's correct. Yeah. So here what we have. So this is multiplication by the order of g in both homotopic to multiplication by the order of g in both directions. So if you're working rationally, so you can invert the order of g, then it's providing an inverse to the transfer map, which is exactly the claim that the cofiber vanishes. Yes.
So you said LTN SP is those with that condition? And
yes, correct.
Sorry, just remind me that LNF is without which condition?
No, LNF is just this condition. Yeah. Yeah.
So in particular, if the order of the group is invertible, you can prove the expected thing that they are inverse invertible. So that's not okay. Yeah. So if
all you need is the order of the group to be invertible, and then the take construction will automatically vanish. Note, by the way, that it's not saying that the take construction of such a spectrum vanishes. You have to take the take construction in the local category. So you calculate the take construction, and then you have to apply this LTN again. So if you want to not, otherwise you have to, you just get this conclusion.
Okay, so then apply LTN again.
Yeah. So implicitly, this is LTN of XTG that's equal to 0.
Also in this, I don't know if it's relevant, but in this infinity thing, there is a philosophy of many higher coherences. So like when you write trace composite self is cardinality of G and F composite space, you can ask whether when you do it, it comes together with all the higher...
Yes, but I do not ask. I do not ask. But I do not ask, and I do not answer. Yeah. Okay, right. So yeah, but for n bigger than 0, it's more shocking. Because there is p-torsion. So, I mean, certainly it's not this same map. You can write down this same map, but it's not going to be proving that trace is an isomorphism. There must be some other mechanism that's explaining it. I'm sorry?
Okay, so this is a kind of elementary case, and then you say that the other one is not clear why. Okay.
Yeah, the other one is much more mysterious, but let's do another example. So another example, so we take n bigger than 0, and let's take x to be En, this Morava E theory, and let's take G to be a cyclic group of prime power order acting on En trivially. This example is Greenlease-Sadovsky. Precursor to Kuhn's work. Okay, so how do we, so the claim is that, first of all, you have the homotopy fixed points, which is the same thing as it's a bit strange notation, but the fixed points for the trivial action is the same as the cohomology of this classifying space. This is also even periodic. Well, it has to be periodic because it's an EN algebra. But it's also even, and it's pi 0 is actually, we have this Quillen formal group for En, which lives over pi 0 of En, and we take its p to the n torsion. And the pi 0 of this fixed points is the functions on the p to the n torsion in this Quillen formal group. Yes?
What is En to the BCP?
Yes, this is the En cohomology of this space. So this is maps from, say, I mean, you could write it like this if you want. Right. So the way you want to think of this is that, so BCP to the n, you can see it as the fiber of multiplication by p to the n on BS1. And then there's some kind of Kunith result showing that the En cohomology of this will be the relative tensor product of the En cohomologies of these. By definition, when you do this, you get the formal group. En cohomology of this gives you the formal group, and then you see the multiplication by p map on the formal group, and you end up with this result here. I'm not going into the details. Also, the Tate construction can be analyzed. For the Tate construction for this, what you do with this, you take the fixed points, and then you just invert a single class. So, and it's actually the coordinate t, or any choice of coordinate for. Another way of thinking about this would be the first Chern class with respect to En, the En first Chern class of the tautological one-dimensional complex vector bundle coming from that inclusion there. Okay, and then in this case, so recall that En has these kind of formal parameters, U1 up to P and then U1 up to UN minus 1. But when you mod out by those, you get a formal group of height n. Oh shoot, I didn't mean to have it be the same n. It absolutely does not have to be the same n. I'm sorry. Yes. Right. So then I'll just say that blue shift, in this case, results from the fact that for a formal group of height n less than infinity over, say, fp to the n, given a formal group G of height less than infinity, we have that the p to the m torsion is connected. So it's a nilpotent thickening of the identity section, in other words, so that when you invert the coordinate t, you're actually going to kill everything when you work mod. So that implies that E t c p to the m t inverse, if you take it mod p v1 up to vn minus 1, you get 0.
No, so I know the group scheme fact, but now you are okay, because you have to, t is the coordinate. Okay, t is like the under this. Okay, so then because you have pi 0 is this, so it is killed when you invert t. No, but then PV, But then you also mod by PV1.
Yeah, so this formal group is the formal group here is the universal deformation of a height n formal group over this guy. But when you mod out by these guys, you recover just the formal group you started with.
Ah, okay.
Yeah.
And then the T is the...
Yeah, exactly. Okay. And so an example of this would be simple example. If you take Ku, which is E1, and then you take the Tate construction for Cp to the m, and you look on homotopy groups, well, let's say pi 0. So it's even periodic, and it's pi 0 is actually just the cyclotomic extension. Fun calculation of Qp. So it's rational because of the Qp there.
So you first complete and then take that construction, or commutes this completion?
Well, I'm not completing, I'm modding out. So it definitely commutes with modding out.
Ah, mod out.
Okay, let me give the proof of Kuhn's theorem. And I'll be essentially giving Kuhn's proof, but there's a shortcut, a substantial shortcut through Kuhn's proof that was in a paper of myself and Akil Matthew. Right. So we're gonna need to use what's called the Bausfield-Kuhn functor. What this is so we have spectra, and we have Tn local spectra, and we have a functor given by Tn localization. And the Bausfield-Kuhn functor is kind of a remarkable, so we have pointed anima, and here's the underlying pointed space of a spectrum. The Bausfield-Kuhn functor is a remarkable factorization of this localization functor through the underlying spectrum, underlying space functor. So it's a very, very strange thing. This, is, of course, only can exist when n is bigger than 1, which says that the Ln localization of a spectrum only depends on the underlying pointed space. If you think of spectra as analogous to abelian groups, this is very strange. It's saying that you can forget the group structure and still recover some completion in localization. It's very weird, but it's possible because we're doing periodic homotopy. So the idea is so let's say n equals 1, then you want to say that like something like this, x mod p and then invert v1, you want to say that that only depends on the underlying pointed space of x. But this is up to a shift. The same thing as taking x mod p is the same thing as taking some mapping space up to a shift from sphere mod p to x. And then you can invert v1 acting here, and then you lift again up to shift. You lift to unstable level. And then you can get a formula for this guy, just in terms of the underlying space. The basic idea is that the v1 periodicity is giving you the spectrum structure. Just like when you put a spectrum structure on Ku, you use Bott periodicity to make it into a periodic spectrum. Here, this operator v1 is automatically telling you what the spectrum structure has to be. So, yes?
Like lifting to the unstable
Yeah.
level. I mean, a priori that only makes sense when like x is finite.
No. You lift this and this. Yeah, not this.
Okay.
You only need to lift those guys. Yeah.
All right, because it's coming from some self map of.
Precisely. Okay, so Now that's the background. This is the key input for the proof, is the existence of this Bausfield-Kuhn functor. You actually don't need to know anything else about this LTN. So step one, there's some general reductions. Like you can reduce to the P group case, kind of very similar to the argument for why it's okay working rationally. You can reduce to a CELO subgroup. And then from the P group case, by a standard reduction, you can actually reduce to CP, standard nilpotent filtration thing. And then you can also reduce to the trivial action of CP on this guy. And this uses the lax symmetry, so XTCP in general is a module over this ring, the take construction of the trivial action on the Tn local sphere. So if you prove that that ring is 0, then also any module over that ring is forced to be 0. This is a trick that comes up all the time. So you really only need to prove this theorem in one case, the trivial action of a cyclic group of order P on the Tn local sphere. Okay, so in this case, so what do we have? Well, the Tn local sphere. What does it mean now to take the orbits of the trivial action on the Tn local sphere? Well, what are we interested in? We're interested in this transfer map. But this is the same thing as the homology of BG. And this is the same thing as, again, BCP, I should say. Yeah. And then we put the cohomology of BCP, and this is, well, some transfer map you have there. And we're also going to contemplate, we have the forgetful map, which just restricting along the base point of BCP. So it gives some kind of augmentation here. And this composition is also called transfer. I don't know. So transfer, maybe transfer prime. So what we want to show, so recall that this is kind of like the inclusion of an ideal. If we want to show that the quotient vanishes, it's enough to show that this map hits some unit. So we want that TR hits a unit, say on pi 0. But this map, epsilon, is an augmentation. Epsilon detects units. So if you have an element in pi 0 here whose image in here is a unit, then it has to be a unit.
What is the notation as, again, the topologist notation, as BCP, but what does it mean?
So it's a spectrum whose homotopy groups give the cohomology of BCP with coefficients in this spectrum.
It's just infinite suspension.
No, this is the dual thing.
No, SBCP
Yeah.
Is something. Is it just the suspension, the suspension spectrum of BCP? No.
I mean, it's like cohomology. I mean, and this is trivial. Say trivial local system.
Okay, but S is for the suspension of BCP.
Which S?
It's on the left side.
Oh, this?
Yes. This is the.
Oh yeah, this is the suspension spectrum. Yeah, yeah. I mean, so maybe I want to. We're supposed to be Tn localizing. Maybe I'll do it like this. We wanted to prove that the take construction vanishes Tn locally. So this guy's already Tn local. So we do have to Tn localize this. That gives this. Okay, so this epsilon detects units. So it's enough to show that TR prime hits a unit. The reason epsilon detects units is it's kind of like a limit of nilpotent thickenings. Like if you write this space as a union of finite CW complexes. Okay. And for this, by the Bausfield-Kuhn functor, it would be enough to show that when you take this transfer map exists without localizing, admits a section up to equivalence, which is the same thing as admitting a section. And you can even check it after looping. After applying loops infinity. And I can even loop an extra time if I want. Because the Bausfield-Kuhn functor, just like Tn localization itself, doesn't care how many Whitehead covers you take. It's going to be making things periodic anyway. So a consequence of the existence of the Bausfield-Kuhn functor is that if you have a map of spectra which admits a section after applying this functor, then it has a section after Tn localization. And this follows from the Kahn-Priddy theorem. Let me give Siegel's proof of the Kahn-Priddy theorem because it's kind of fun. So
this, what is omega infinite? No.
So this is underlying pointed space, and then I take loop space once more. In other words, yeah.
Because, okay, you have omega, and then why is it enough to take loop once more?
Because the Bausfield-Kuhn functor will actually send loops to loops. It'll send loops to the Bausfield-Kuhn functor sends loops to desuspension. So we're trying to use the Bausfield-Kuhn functor to make a map between the Tn localizations of some spectra. The Bausfield-Kuhn functor says it's enough to produce a map on underlying pointed spaces, right? But this loops of loops infinity is just the underlying pointed space of the desuspension, of your spectrum x. So by the Bausfield-Kuhn functor, you'd get a map from the desuspension of x to the desuspension of y, but then you can just suspend again, and you get a map from x to y. So this is fun. So we maybe know that sphere spectrum is what you get when you take the category of finite sets and you group complete it. So this is finite sets under disjoint union. Maybe slightly less well known is that similarly, this has a description. You take finite free CP sets up to isomorphism under disjoint union, and then you group complete it, and then you get this. And this transfer map is just induced by the forgetful functor. Now, we're going to make a map backwards, which will essentially give the splitting. So for S a finite set, we can form a p-fold Cartesian product and remove the diagonal I mean, the thin diagonal, so just the copy of S. And this is then going to be a finite and free CP set, because we removed the CP fixed points. Now, this is not going to give and induce a map on K-theory spectra. So this is not additive. This doesn't send disjoint union to disjoint union. So you won't get a map of spectra backwards, but it's polynomial in some sense. It's a polynomial map. Well, intuitively of degree p, and that's good enough to induce a map not on the level of the group completion as spectra, but on the level of the underlying pointed spaces. It's fine. Or maybe unpointed, but we can always shift by the base point. Okay. Now, is it a section? Well, no, not really, because when you take S to this and then forget, well, you're doing S goes to S to the P minus S. But so the induced map, the composition, so that's a map from loops infinity S to loops infinity S. Well, what is that map? It's the map in terms of the ring structure. It's like alpha goes to alpha to the P minus alpha. So it's not the identity. But alpha goes to alpha to the P is 0 on homotopy in positive degrees. So after applying loops, alpha goes to alpha to the P minus alpha is an equivalence. Oh, it's actually a general fact about ring spectra. I mean, so you can check it, for example, on the free ring generated by a, so like even associative ring generated by a class in degree whatever 5. Then that class in degree 5, I mean, it's just going to have something there, and then it's going to have something in degree whatever 25, which represents the square. And then the squaring map will just hit 0. Well.
The squaring map does not change the degree.
It doesn't change the degree.
Okay,
yes.
so it is natural to think it should.
Yeah. Yeah. Okay. Yeah, so that's actually a proof. Very strange. Yes?
It's a polynomial map. Okay, so it doesn't induce a map of like commutative groups in spaces.
Correct.
But it induces just a map of space.
Exactly.
And that's all we need.
That's all we need. And that's all we can get, because if it induces a map of spectra backwards, then we'd be proving that Tate always vanishes. But it's not the case. Yeah, so this is funny, but it's a proof. Let me make a couple of remarks about this Tate vanishing. Or well, yeah, so this Tate vanishing implies that this x goes to x Tate CP. Well, as long as you take it modulo some PV1 up to Vn minus 1, no, sorry, not the Tate, that vanishes. But that when you take the homotopy fixed points, well, that's the same thing as if you did homotopy orbits. And it's a funny thing that some limit construction should agree with a colimit construction for arbitrary x. And it actually implies that x goes to xcp mod p v1 vn minus 1 has is essentially a finitary operation. So let me say maybe more precisely what I mean by that. So for example, so this x, so this is now in fun BG TN local spectra, going to x CP, the homotopy fixed points mod P V1 Vn minus 1. This functor lies in the thick subcategory generated by just the functor x goes to x mod P V1 up to Vn minus 1. So somehow you can build the fixed points of a CP action functorially in terms of the underlying guy in just finitely many operations, as long as you allow retracts. So for example, when n equals 0, this is familiar, like xCP, or it doesn't have to be CP, I'm sorry, it could be a G, you know? Xg is the image of an idempotent, this, you know, on X. And so that's directly a retract of the underlying spectrum. For n equals 1, I actually have no idea how to make this explicit. It's kind of an existence result. I would very much be interested in knowing what the formula is for the fixed points. There should be some finitary formula for fixed points. I don't know how to figure that out. It's just, it has to exist, some formula like that, but I can't write it down.
Yeah, but you can prove it exists by doing somehow work, I mean, looking at it in some universal.
Exactly. Yeah, exactly. Yeah, you look in like G objects in this local category, and you want to prove that the trivial action is like a compact object, which is a consequence of the Tate vanishing. I mean, at least modulo these guys. And then it has a finite resolution by free things, and then that is what gives you this kind of conclusion. Yeah. I won't go into the details of the proof. Okay. Yeah, and another thing, also, so similar, the homotopy, like the homotopy fixed point spectral sequence for calculating, you know, this addresses Ofer's question from last time about virtual cohomological dimension in Thomason's theorem. The homotopy fixed point will collapse at a finite page. With horizontal vanishing line. So, although in principle the group cohomology of G acting on the homotopy will contribute to the homotopy of the homotopy fixed points, after some range of cohomological degrees, all of those classes will be killed by differentials in the spectral sequence on some finite page. So it behaves as if, even though a finite group always has infinite cohomological dimension when it's non-trivial, it'll behave as if it has finite cohomological dimension when you look at one of these spectral sequences.
So what is the homotopy fixed point spectral sequence? First, there is a spectral sequence involving the cohomology of G acting on the fixed point.
Yeah.
Okay. So,
Yeah.
Okay, and then what the collapse means exactly?
It means that the differentials will all be 0 after a given page.
What does it mean, horizontal vanishing line?
So what I mean is that on the on like the E100 page or whatever, you'll have, so we have the term EPQ. EPQ will be 0 for P large enough.
So it's HPG actually pi minus Q or something like this.
Yeah, or I mean, I did it the other way around, so I don't know. I mean, but in any case, I mean that the terms that come from high cohomological degree of group that come from high degree group cohomology will eventually be killed in the spectral sequence.
There are two ways the spectral sequence can collapse. I guess either for some complicated reason the differentials are just zero, or there could literally be no room for differentials because everything's zero.
Right.
And that's what we mean, right?
No, I mean for some complicated reason. It's not for degree reason.
No.
Yeah.
But it also
vanishing line.
Yeah.
It's not above the line, everything is zero.
No, that's what it means, yeah.
Okay, yeah.
It means on some finite page, above that line, everything is zero.
Okay, yeah, no, that's the...
And then there is no room for differential.
Yeah.
Then there is no room for the differential to be non-zero.
Well, that's true, yeah. Yeah.
Okay, so it's not like the spectral sequence. It's an example like the spectral sequence for a formal scheme, like in EGA, which vanishes for trianity reasons, because you have ascending sequence, but it doesn't mean that it doesn't have this property. No, this is just a standard application of spectral sequences in EGA. When you compute the cohomology of formal scheme relative to dyadic topology in terms of the cohomology of the associated gradients, so let's say just a coherent sheaf on a formal scheme or a complex.
Yeah.
In any case, then you get those connecting maps. The point is that there it is just a trianity, and it doesn't mean that things will become zero.
Okay.
But here there is no room for differentials. It collapses for what is like what is said for the strongerism.
Right. Okay. All right. I believe that I agree with everything that's been said. All right. But yeah. Okay. Fine. So that was the proof of Kuhn's theorem. I wanted to present it because I do feel it's a crucial aspect of chromatic homotopy theory. And in some sense, it's blue shift, it's opposite to redshift, but it's actually used a lot in proving redshift. So, in several different ways. Okay, so let's give proofs, proof of descent and vanishing. So more precisely, the claims, so if A is an ordinary ring, then LTN of the K theory of A is equal to 0 for n bigger than 1. So this was the Mitchell theorem. So this is what we're trying to prove. And then the descent, so A to B, G Galois, extension of commutative rings, ordinary commutative rings, then LT1 K of A, LT1 K of B, G. So this is Thomason. I'm doing the kind of classical analogs of these higher height theorems, but with proofs that basically are the same proofs that establish the higher height versions.
Do we want G to be a P group or P?
It doesn't need to be, but
The CMN.
yeah. Okay, and actually, the way we prove this is by making a third claim which implies both of these. And in general, the proofs in this CMNN paper are actually you kind of prove both vanishing and descent by some induction on the height, where it's kind of like going up a spiral staircase. So vanishing implies descent, implies vanishing implies vanishing, implies descent, but each time you go up a height. So somehow it's an induction on the height, which is a little bit interesting. And hopefully that will be apparent. The mechanism for that will be apparent in this discussion. So the more primitive fact is, it's a more primitive. So if you take K theory of Z, and then you take CP orbits, then there's another kind of transfer map here to the K theory of representations, so to speak. So fun BCP perf Z. This map is an isomorphism T1 localization. So I claim that star implies both vanishing and descent. So
do we mean K of Z group ring CP inside?
Group ring BCP. I mean,
the co-limit over
BCP.
Yeah, but in particular, it's literally K of Z adjoin CP.
No. This is on the outside. Yeah. Okay. So star implies Thomason. So the first step is to reduce to the P group case. And then the second step, so it's just like in Kuhn's theorem, reduce to G equals CP. And the arguments are very similar. But the key mechanism is to use the transfer map. So you have a transfer map. So you certainly have a map from K of A to K of B, which comes from the extension of scalars, but you have a map backwards, induced by the forgetful functor.
And the composition is multiplied by the class of B in K0.
That's right. But yeah, but this is also G invariant. So it induces a map from K of B homotopy orbits to K of A. And the cofiber of this transfer map, just like our discussion of Tate cohomology, this is multiplicative. So this is a ring. And in fact, the cofiber of the comparison map, K of A to K of B fixed points, is a module over it, this ring. And the same is true after applying any localization. Anywhere you like, actually. You can apply it. So what this tells you is that it's enough to show that LT1 cofiber of the transfer map is equal to 0. So you have to prove descent, it's enough to prove the claim that's sort of dual to descent. But it's better to think of the claim dual to descent, because it's more robust due to this ring structure you have on the thing you're trying to prove is 0.
So now with the co-invariant stuff.
Yes, exactly, with the co-invariants. Yeah.
You don't have the X, okay.
And I need to use the co-invariants. Otherwise, I'm actually not sure about this ring structure, in fact. So, okay, but star is the same thing, same statement. Same statement as this, but for, say, so you replace perf B with this G action, you replace by perf Z with the trivial action of CP. And perf A, which the only thing you need to know about it for this whole argument is that it's the fixed points for G acting on perf B. That's kind of Galois descent. That gets replaced by fixed points for the trivial action, which is just the same thing as representations. So functors from BCP to perf Z. And just like in the proof of Kuhn's theorem, where we reduce the case of an arbitrary G action on an arbitrary spectrum to the case of the trivial G action on the unit, this guy, so this is actually a module over this guy. This category with a G action is a module over this category. Well, let's say if it's CP, yeah, is going to be a module over this one. So in fact, so cofiber transfer in general is a module over cofiber of transfer as in star. And that finishes the proof that star implies Thomason. So basically you generalize the statement of descent to a claim about any category equipped with a G action and the homotopy fixed points for that category. And that claim reduces to the case of the trivial action, where it's exactly this statement about K-theory of representations. Okay, let's take a 5-minute break.
So you need somehow to know the cofiber is a ring.
Yes.
Of course, intuitively, like the image is like an ideal, but here we need much more.
Yes.
We need to, is it like an infinity ring?
Yes, it's an infinity ring.
So you need a lot of things that, what do you have to verify?
You use the machinery of equivariant stable homotopy theory. So you make an equivariant G spectrum, a ring object, which corresponds to, it corresponds to K-theory of B with its G action, but where the fixed points is K of A. And you can make this using some machine with transfer maps. Well, okay, yeah. And then this cofiber of the transfer is it coincides with a construction called geometric fixed points in the land of G equivariant spectra. And just like and it's similar to Tate construction, except instead of taking the homotopy fixed cofiber of transfer to homotopy fixed points, you're taking cofiber of transfer to honest fixed points. And there's an explanation for why geometric fixed points is lax symmetric monoidal, which is parallel to an explanation for why the Tate construction is lax symmetric monoidal. So both can be viewed as Homs in some quotient category. Quotienting by the free G guys.
So this is very complicated.
Yes.
Okay, so it's not, you need two occurrences, but if you don't have the G, so you just say KB to KA, of course the image is an ideal, but the ring thing will fail. I mean, because if you don't have all this machinery you're hiding
Exactly.
that allows you really to prove it.
Exactly. Yeah. No, it's complicated. Yeah, I agree. Okay, we'll take a 5-minute break. Now I'll discuss why star implies Mitchell. So we use a lemma, which again uses this blue shift idea. This is basically due to Hahn, but maybe in this form it was in our paper, Jeremy Hahn. So let's say R is an infinity ring. Then if the Tn localization of the Tate construction, now whenever I have a Tate construction without specifying the action, it's for the trivial action. Okay? So if this is equal to 0, then LTn plus 1 of R is equal to 0. So this is, philosophically, this makes sense from the perspective of blue shift. So when you blue shift, you're supposed to go down by 1. So then if that was 0, then you shouldn't have had anything already at height n plus 1. And thankfully, such claims are now much easier to prove. So let's give a modern proof, so to speak. It's not a very old result, but now the big breakthrough that makes such things easier to prove is this chromatic Nullstellensatz. Which is another result I wanted to be able to mention, which is one reason I'm presenting this. So this is Burklund-Hahn-Levy-Schlank Yuan. And one consequence of this, the results in this paper, or one result in this paper, is that if R in C-alg a Tn local infinity ring, so if it's not 0, then there exists an algebraically closed, say, field K of characteristic P and a map, a homomorphism from R to the Morava E theory for that field, say based on the Honda formal group. So you're supposed to think of this as analogous to the following well-known fact. If you have a non-zero commutative ring, then it admits a homomorphism to a field, algebraically closed if you like. In this setting, the funny thing is that you get not just a map to a field, but you automatically kind of get a map to what behaves like a formal thickening of a field. This is a little bit potentially surprising at first glance. So for example, a consequence of this is that this Morava K theory, which was the thing you get by modding out by a bunch of stuff, that can't be an E-infinity ring. Because if it were, it would kind of, you wouldn't be able to map backwards to a Morava E theory. So this is a important...
What could not be an E-infinity ring?
Morava K theory, like the residue field of this complete local ring, so to speak, actually can't be an E-infinity ring. Well, I mean, it would actually, well, because then it wouldn't be able to map back to a Morava E theory, because it's a quotient of a Morava E theory. It's never going to map back. This is not something like this. I mean, actually, literally, you can use this to disprove it, but never mind. I just want to give intuition. I'll keep this statement, but. So how do we use this chromatic Nullstellensatz so we can prove the contrapositive? So if LTn plus 1 R were non-zero, then there exists a map from R to some En plus 1, well, say Ek Hn plus 1. And then we can check, again, via this Greenlease-Sadowski that I already mentioned, that Ek Hn plus 1, if you take Tate Cp and then Tn localize it, there is something there. So we said when you Tn plus 1 localize this, you get 0. That was the Tate vanishing argument in Greenlease-Sadowski. But if you look at the next height, there actually is something there because of these other formal parameters in the Morava E theory. So this would contradict, but the Tn localization of R Tate Cp maps to this. But just by functoriality, so we get a contradiction. So if this were 0, then any ring that this emits a homomorphism to would also be 0. But it's not. You can calculate it, and it's not 0. That's the... So I hope blue chalk. Well, no, I'll do pink chalk. It's just that I prefer colored chalk to non-Hagomoro chalk. So, Hagaromo. Oh, I've been pronouncing that wrong my whole life. Okay, so we're back to star implies Mitchell. Is this okay? Is this okay? The color? It's not good? Okay. I'll try blue. Oh, there's a... okay. All right. Okay. So star implies Mitchell. Right, so recall that that is star. But, okay, so this K of fun of CP perf Z, so recall the interpretation we had as the K theory of perf Z CP, the fixed points of the trivial action on perf Z. This certainly maps to K theory of Z with the fixed points there. No way, thank you so much. Oh, yeah. Yeah, so that certainly maps there, and similarly, for similar reasons, the cofiber of the transfer in star maps to K of Z Tate construction. So they're both cofibers of, or I mean, as a consequence of this, and in fact, both of these are E-infinity rings. And this is an E-infinity ring homomorphism. So LT1 cofiber of transfer equals 0, then implies LT1 K of Z Tate CP equals 0, and then that by the lemma implies LT2 K of Z equals 0. But then if you imply the lemma again, so certainly if this guy is 0, then any Tate construction on it is also 0. Then you get LT3, K of Z equals 0, and then etc. So yeah, it's some kind of magic, I don't know. Okay. Now let me give the proof of star. So, well, a sketch at least. Oh, we can replace Z by Z1 over P. That's by this purity result. I mean, we can actually, if we want, we can throw in a P power root of unity by, because this is an extension of order prime to P, and we're interested in P information. But then, fun BCP perf Z1 over P. Once we're inverted P and we have all Pth roots of unity, this category is actually just a product of copies, of P many copies of perf Z1 over P zeta P. So the representation theory, just like you're familiar with, the representation theory of a cyclic group, once the order of the group is inverted and you have enough roots of unity, it's just an isotypic decomposition. Yeah?
In this proof of star implies
Mitchell, yeah.
It was a statement about the general ordinary ring.
Right.
So you used some facts like K theory of general ordinary ring is a modulo over K.
Oh yes, thank you, yes. I forgot the first step is it's enough to show it with Z, because any K of A will be a module over K of Z. Yes, thank you very much. That should have been the first step, yep. Yes. Right. Yes, so then that implies that K theory of this is free of rank P as a K of Z1 over P ZP module. And that implies that when you take K theory of this again, and you tensor it with K1, so the first Morava K theory, this is free of rank P as a K1 tensor KZ1 over P zeta P module. But if you take K of Z1, we look at the left-hand side, K Z1 over P zeta P, CP fixed points, tensor K1. Well, you can rearrange this. It's K Z1 over P zeta P, tensor sphere, or K1 BCP, is also free of rank P as a K of Z1 over P zeta P tensor K1 module. This time, because this guy is free of rank P as a K1 module by the dual to the Sadovsky, Greenlee-Sadovsky computation we already mentioned, and the fact that the P torsion in a height 1 formal group, the functions on the P torsion in a height 1 formal group is free of rank P as a module over the commutative ring you're living over. So we have, in this transfer map, it's actually, once you tensor with K1, it's a map between two free modules of the same rank. But it also has a section. So has a section by Tate vanishing. Induced by the exact same thing that the right-hand side maps to the fixed points. So when you go, and this map is the transfer map appearing in defining the Tate construction, so it's an isomorphism when you tensor with K1. So we have a map of free modules of the same rank which admits a section, so it has to be an isomorphism. Tensor K1, and then that also has to be true when you tensor with T1 for one of several arguments. Yes, please.
What was
Yeah.
K1?
K1 was the Morava K theory. Yes, so this was E1. It's just E1 mod P. It's the same thing as KU mod P. Mm-hmm. Right, so T1 is this.
But this is something that was already known, like the telescope conjecture.
Yeah, so one argument for this is that the telescope conjecture holds at height 1. But another argument is that as a consequence of what's called the nilpotence theorem, the property of a E infinity ring, or any ring really, E1 is fine, being 0 after Tn localization is equivalent to it being 0 after Kn localization. That argument works at arbitrary heights. Okay. So the question of whether a ring vanishes Tn locally or Kn locally is the same question. Okay.
So that's the final step.
Yes.
What do you mean that the co-fiber of trace has a section?
I'm sorry. I just mean that trace has a section.
Trace tensor K1 is an isomorphism.
Yeah, I'm so sorry. It's 0. Yeah. Yeah, I'm so sorry. Thank you, Matthew. I was rushing because of the time. But, okay. Okay. So there are some corollaries of this that are important, some corollaries of these soft theorems that are important for this telescope conjecture business. So one is that for n bigger than or equal to 1, I already mentioned this before, you only need the previous two. Only need the previous two guys. Second, also for n bigger than or equal to 1, this will partly address Ofer's questions from before the lecture. You can actually pass to the connective cover of any of your ring A before taking K-theory.
Here you wrote the last thing is LTN10 direct sum.
Tn direct sum Tn plus 1. So in principle, you need to include all of the previous Ti's, but actually you don't have to, because of the vanishing result, you don't have to include the ones that are two or more away. Yeah. 3 also for n bigger than or equal to 1, if A is connective, then LTn plus 1 K of A TC of A give the same answer. And I'll mention another fourth one. So A going to LT, again for n bigger than or equal to 1, LTn. So this is all special features of height 2 or higher algebraic K-theory. Yes, yes, exactly. So this is this functor preserves sifted colimits. So that's equivalent to saying it preserves filtered colimits, which is clear, plus geometric realizations, so colimits over delta op. So proof. So 2 follows from the fact that tau greater than or equal to 0. 2. Well, we already gave the argument for 1. I won't revisit it. So this induces an isomorphism on LTI as long as I is bigger than or equal to 1. Because once I is bigger than or equal to 1, you're periodizing. So then when n is bigger than or equal to 1, you're allowed to apply periodic localizations to A, so you're not seeing the difference between A and its connective cover. For 3, oh boy. For 3, so you use Dundas, Goodwillie, McCarthy. So first of all, I'll say it in words. This TC it's important to know what this is. It's sort of like K-theory. It receives a map from K-theory. But it's different from K-theory in that, recall. So one of the difficult things about K-theory is that it's built from general linear groups over your ring. So that's, yeah. But TC is different. So TC of A is just built from your ring. Via tensor products, colimits, and limits. So instead of being built from the general linear group of your ring, it's just built from your ring itself and its tensor powers, using some complicated formula which uses the ring operation on A. So and because of this, it's kind of more closely related to differential forms. So yeah. So it's much simpler than K-theory, even though it's still quite complicated. OK, so Dundas Goodwillie McCarthy says that so if A is connective, then the difference between the K-theory of A and its pi 0 is the same thing as the difference between TC of A and its pi 0. So, and then use Mitchell vanishing.
And does it also work for nilpotent ideals?
Yes, it does.
And is it for associative rings? Or?
Yes, it's for associative rings. For a connective, a E1 ring. So it's in algebra, connective spectra. So the difference between these guys is the same as the difference between these guys, but these guys will vanish at heights bigger than or equal to 1 by the result, by Mitchell's result. And then 4 follows from 3. Plus easy properties of TC. So TC itself commutes with geometric realizations and, well, close enough. Let me say up to epsilon. Yeah, and then you just use that. So I won't give the details. Okay.
This vanishing of TC, like height greater than 1, is also proved in the same way or something.
Right, so it's still a module over K of Z. So TC is also a multiplicative theory, and as a multiplicative theory, it receives a natural transformation from K. So TC of any ring will also be a module over TC of Z, which is a ring which receives a map from K theory of Z. So it's a, yeah.
3 also hold for a non-connective?
No. Very important point.
Yeah, like everything to use 2.
Yeah, so warning. So yeah, if you can combine 2 and 3, so that LT n plus 1, so for n bigger than or equal to 1, K of A is equal to, let me just write is equal to, be a chain of equivalences, right? TC of the connective cover of A, but LT n plus 1 K theory of A is not isomorphic to LT n plus 1 TC of A. You really have to take the connective cover before you go to TC. And the reason is, so say if A is, say, L and F local, then so is TC of A. Because the L and F category is closed under all of these operations. Tensor products, limits, and colimits. So you wouldn't have so you wouldn't get redshift. If this were true, if it were true that these were equal, then there would be no way for redshift to hold, because you'd be stuck at heights less than or equal to n. This is a very important point. So really, this redshift is quite remarkable. I mean, the fact that it can happen is quite remarkable.
So TC. Then you would get 0 on the right and no.
Yes, you would get 0 on the right-hand side. Yeah. But we know, oh, no, redshift happened. So actually, let me make that point. So converse of vanishing. So this is this result of U1, and then, again, the one-line argument once you have the Burklund-Hahn-Levy-Schlank U1 extends it to the general case. So if R is in C-alg spectra, then LTN of R, if this is non-zero, then LTN plus 1. The K-theory of R is also non-zero. And well, let me just say one. I don't want to discuss the borderline cases. So this is saying that the redshift really does happen. So the vanishing was that if this is 0, then this is 0. But here, if this is non-zero, then this also has to be non-zero. So there really is something at the next height. So redshift really does happen. I just want to give an idea of the proof. So what Yuan actually showed is that if LTN, say plus 1, of R is not equal to 0, then LTN plus 1 of something else is non-zero, and it's the K-theory of the Tate construction, again for the trivial action. So this is a very clever idea. He said redshift is hard to establish because it's hard to see why you have to go up a height. But blue shift takes you down a height. So composing blue shift and redshift, you're staying at the same height, so it should be easier to prove. You're just proving that something stays at the same height. So that's what he does. He says if this one has information at height n plus 1, then the Tn plus 1 local K-theory of the Tate construction also has information at height n plus 1. And the way he does this is basically he produces a map using like TC or related things. He makes a map to this so-called S1 Tate construction on R. And then he shows that this is also non-zero whenever R is non-zero. So you don't have blue shift for S1 Tate construction, which is, it's also something you easily see for Morava E theories, that it just becomes a power series ring or a Laurent series ring, and so it stays the same. Okay, and then, also Yuan, if you take En, so we can apply this to En plus 1 Tate CP, so this is locally, so let's say a tall hyperlocally, well, a tall locally an En algebra. It's not quite as simple as this. So then he deduced redshift, so LTN plus 1 KEN is not equal to 0. And then Burklund-Hahn-Levy-Schlank Yuan just apply Nullstellensatz again. So using a tall descent from CMNN and the non-triviality here, you can deduce the non-triviality here. And then using the Nullstellensatz, you get the non-triviality in general. Okay, that concludes my discussion of soft theorems. Are there any questions?
For the first theorem, yeah, it's for LTN minus LTN, or it's LTN?
Where?
The first line of the proof.
Of the proof? No, this is Tn plus 1.
Okay,
but then this guy is going down by height, down in height.
Oh, it's going down and then going up.
Yeah, exactly. You blue shift and then red shift. Yeah, that's the key idea. Yeah. Other questions? Okay.
So not exactly about the proof, but
Yeah.
So the result that this new result that you have with Burklund.
Yeah.
Just to put it into context. So for this, for these like descent results, we can generalize these to like whatever higher semi-additive descent.
Okay.
Can you, where you have like pi finite p spaces?
Oh yeah, we didn't think about that. Yeah, we only thought about just usual groups.
It's also not apparent what like a good notion of like a Galois extension is in this case.
Yeah, I haven't really considered it. Yeah. Okay. So maybe this I think this does a good job explaining like why redshift happens, especially ones. This argument here is very short, easy to read. I recommend his paper very strongly. But it maybe doesn't explain exactly how redshift is happening. Like it's very like because it's so soft. So there's something now something a little stronger or much stronger is something called the Quillen-Lichtenbaum property. So definition, let me take n bigger than or equal to 1. So let me some notation borrowed from the telescope conjecture paper. So this means so when I write x in SP plus, I mean that the homotopy is 0 in sufficiently negative degrees. So an x in SP plus satisfies, let's say, QLN if x mod p v1 up to vn. You also mod out by the last one if pi star of this equals 0 now for star greater than 0. If you combine with the hypothesis that x is an SP plus, you see that, in fact, what this means is that the homotopy of this guy lives in a bounded range. So there's also FPN. This is Mahold-Resk, which is QLN plus each homotopy group is finite. Finite cardinality. That's a okay. So let me make some remarks. Well, first remark is that it's independent of the choice of p v1 up to vn. That's as usual. The second remark.
P, there is not much choice in P.
That's true.
You can take powers of P.
You could also take powers of P. Maybe that's what I mean. Yeah. A V0, so maybe I should say V0. So V0 means a power of P. Or something whose power, one of whose powers is a power of P. Okay, whatever. Right. Second is that QLN implies that if you take the Ti localization of x, then you get 0 for any I strictly bigger than n. Because, well, when you do this, if you invert Vn plus 1, you're going to get 0 because, again, it's living in a bounded range of degrees and you're inverting some periodicity operator, which grabs from higher and higher degrees. But also, so QLN gives good control. So it vanishes at height bigger than n, but it also gives good control over what's supposed to be the interesting height, which is the height just before it vanishes, LTNX. So let me make this precise. So more precisely, claim, and this is actually one of the main Burklund-Hahn-Levy-Schlank. So these guys in this telescope conjecture paper, this very simple observation is one of the main points in that paper. So suppose if x has QLN, then there exists a Vn self-map. So there exists a choice of, let's say we fix P up to Vn, then there exists an A greater than 0 such that the homotopy groups of X mod P V1 Vn minus 1 and then invert Vn are a functor of the homotopy groups of X P V1 up to, Vn to the A. So after changing which Vn self-map you're considering by raising to a power, then you have this somewhat paradoxical seeming property that the homotopy groups, when you invert Vn, are completely functorially determined by the homotopy groups when you mod out by Vn. Very strange, because normally you think but just there is a fixed power. And functor, I mean, in X satisfying QLN with a fixed range of degrees. So C prime. No, X mod P up to Vn is in some range. Yeah.
X is an SP
Yeah.
plus.
X is an SP plus with X mod P Vn in a fixed range of degrees. So by QLN, it lives in some range of degrees. If we fix that range of degrees, then I'm going to describe the functor that gives this.
And I guess would the argument be something like you run like this?
Well, I'm going to give the argument. So. So, okay. So note that, so proof. So note that, well, so let's say Vn has degree d. So it's a degree d self-map. So then you have sigma d. Let's let y be, we're not changing the previous guys, so we let y be this X mod, the Vn minus 1s. So if we look at this, so this y mod Vn is the thing that we have the hypothesis on that we live in this range of homotopy. Now y is connective, so the bottom homotopy group of y, well the bottom homotopy group of this will be higher than the bottom homotopy group of this. So the bottom homotopy group of this is the same as this. And what we deduce from this, first of all, is that y is also has the same, so y starts at the same point as y mod Vn. But also, yeah. And then if we let's look at iterates of this. So sigma day Vn to the a y mod Vn to the a, we deduce that the map from y to y mod Vn to the a is an isomorphism in degrees less than or equal to. So this one, y starts at degree c, then this d8th suspension of y starts at degree c plus dA. So. On the other hand, we also deduce from this Vn, y mod Vn. So the homotopy of this stops at degree c prime. So Vn is an isomorphism in degrees bigger than c prime. And then that tells you that y going to y with Vn inverted is an iso in degrees bigger than C prime. So then we look at this diagram. So we have y goes to y mod Vn to the A, and then y Vn inverted, which would also be the same as y Vn to the A inverted. It doesn't matter. So now we choose an A so that C prime plus A times D is greater than or equal to C plus D. So we had this is an iso in the range C to infinity, and this was an iso in the range C to C plus D by this assumption here. So we deduce that pi star y Vn inverse is the same as pi star y mod Vn to the A for star in this range C to C plus D. And then by periodicity, this determines pi star y mod Vn to the A in general. Sorry, but y Vn inverted in general. And that's the proof. So this is very important, this Clausen-Lichtenbaum property, because you get sort of especially if you have FPN, you get sort of you have a finite amount of information that completely determines the Vn periodic homotopy.
I'm confused with
Yes.
degrees.
Yeah?
So the above, the horizontal map is isomorphic in degree C prime to infinity, right?
Must be, yeah. CC, did I say CC prime? Yeah, maybe I got my C's and my C primes mixed up. Yeah. Maybe I'm confused about degrees.
And the vertical one is isomorphic in C plus AD, right?
Yeah, I chose C. Did I get my C's and C primes confused? I'm very sorry. Okay, so that's definitely true there. And this is in degrees C to, what did I say over there? C plus dA, yeah? Okay, I want to make it bigger. Yeah, there we go. So C, sorry, I got my C's and C primes confused. Thank you very much, and I apologize. So in particular, C prime plus D. Wait, C. Yeah, C prime, yeah. So in particular in C prime, okay, I hope I got this right now. Yeah, so C prime. In any case, once we get the homotopy of this in some range of D consecutive, or D plus 1 D consecutive degrees, then we know it in general because of periodicity. And in some range of degrees, it's going to be the same as this once you make A big enough. That's the idea. Yes, I got my C's and C primes mixed up. I apologize. Okay. So, right. I should now, so this is obviously a great property if you have it. But when is it true? So maybe most classically you have QL1. Well, let me just, let me not try to give perfectly, so if you take the K theory of a field F, so F has characteristic different from P, and the cohomological dimension of the Galois group of F is less than infinity. So that's maybe Voevodsky. And this is kind of the classical situation for the Quillen-Lichtenbaum conjecture.
What was the classical Quillen-Lichtenbaum conjecture you referred to?
Okay, let me, yeah, so, okay, you know what? Let me give the quick argument for this, and then it'll maybe make this more apparent, and then I'll pick up the other examples next time. So, so there's a motivic filtration. Oh, F and F, I apologize. With associated graded, so GER D, K of F, is this motivic cohomology in weight D, shifted up to 2D, shifted up 2D. And then we have a small claim. So what we want is that if we take K of F mod P and we map it to K of F mod P and then invert V1, which is LT1 K of F mod P, we want this to be an isomorphism in high degrees. So the claim, so K of F mod P to LT1 K of F mod P promotes to a filtered map. With respect to the Étale-Postnikov filtration. On the right-hand side. So recall from Thomason's theorem that this is an Étale sheaf. So we can consider the Étale-Postnikov tower. You take the Postnikov tower section-wise over the Étale side of F, and then you Étale sheafify that. And it promotes to a filtered map. This is actually for formal reasons. The Étale-Postnikov filtration has a universal property of being connective. So it's because if you take Z mod P, a standard property of the motivic complexes is that when you Étale sheafify them, since we're in fields of characteristic different from P, when you Étale sheafify the motivic complex, you get Étale cohomology. So you get the usual Étale. So let's say the Étale localization. And that is indeed, it does live in degrees. Sorry, double speed. So this lives in degrees greater than or equal to 2D Étale locally. So that automatically means you get a map. And then the further claim on associated gradients, this map is the canonical one, is the canonical. So Z mod PD, that's the motivic Z mod PD mapping to the Étale Z mod PD. The usual Tate twist. And this follows by multiplicativity. plus easy calculation in weight 1. Which one has to do? Yeah. No, it's easy. You go to a separately closed field, and it's very simple. Yeah. Because these are both concentrated in degree 0, so it's really elementary. Okay. Now the key thing is the theorem of Vojevodsky. So is that this Z mod P D can actually be recovered from its étal. So this object on the étal side of F is just the truncation in degrees bigger than or equal to minus d of C mod P D étal. So let's say as presheaves on étal side of F of spec F. So in other words, the motivic cohomology is just a truncation of the étal cohomology. You truncate in cohomological degrees less than or equal to the weight. So that was the Beelenson-Lichtenbaum conjecture. And what this implies is that if F has finite cohomological dimension, then ZPD maps isomorphically to ZPD étal for high enough weights. All right, maybe I shouldn't be using D. Well, no, I guess it's okay.
But is that in fact what you're going to need?
I'm sorry?
Is that in fact all you need?
That's all you need, yeah. So then, yeah, because then you see that on associated gradients for but then since these guys are living in degree 2D in the motivic filtration, so then as GRP is ZPD, and then it's shifted up by 2D, this means that, so K of F mod P LT1 K of F mod P iso on GER in high degrees. And then that means it's an iso in high degrees.
So you need something about the convergence of the motivic filtration on K field.
Yeah, you need to know it's a convergent spectral sequence, but that's also, yeah, I mean, it follows from, well, yeah, I mean, you need to know it's convergent. There's no doubt about that. Ooh, I went over time. Please accept my apologies.